So this is the website. In this website, you can see here we can there is one side where we can say number of bits. Number of bits could be 3, number of bits could be 2 or 4. So let's say if number of bits are 3, so then it could be represented using 0, 1, 2, 3, and then minus 4, minus 3, minus 2, minus 1. Okay, and similarly using 4 bits. So there are 4 ways of representing here which has been shown. Let's quickly have a recap here. These are the positive numbers which we discussed first, that 0, 1, 2 up to 15. Okay, so this is the positive number circle. If we are doing it in a signed manner, then we see this discontinuity is happening at 2 places. So we are doing 0, 1, 2, 3, 4, 5, 6, 7, and after that, because this 1, 0, 0 is, this is a sign notation, sign magnitude. So basically 1 here means negative number, and the rest of the 3 bits represent magnitude. So you see there is a discontinuity. From 7 we came here to 0, and similarly here this is a negative number, and if I add 1 to it, then it becomes 0, 0, 0. So there is a discontinuity here also. So essentially in a signed representation there are 2 discontinuities, and a representation works like this. In 1's complement, you again see there are 2 issues. One issue is that there is a discontinuity here. So if I add 1 here, from 7 it became minus 7. This is a continuous thing. Minus 7 adding plus 1 is minus 6, adding plus 1 is minus 5. So that means going in a clockwise direction is addition. But here also this is not discontinuity, but this is a kind of an error, that this is also 0, this is also 0. There are 2 zeros in the same number circle, and this is how we can see 2's complement. So if you want to play a bit, you can play using this particular website and have some fun. Okay, so let's get back to the presentation. And so now after understanding it from the number circle perspective, let's have some theoretical background, or let's have some mathematical representation of this number circle, or this particular type of number representation. This particular number representation is called 2's complement. Why it is called 2's complement, we'll see. So here I can mathematically define it, that if a number is u, then its magnitude is representing 2's complement. If number is negative, then 2's power n minus magnitude of u is actually 2's complement. Because it is 2's power n, so it is called 2's complement. And since 2's power n, 2's power, we can also represent this using inversion, or inverse, or logical invert of u, and then plus 1. So this is an easier way to find out 2's complement. So we can invert all the numbers and then add 1. That would be the 2's complement representation of any negative number. So as seen from our circle lines or number circle, we see couple of properties here. One property is there is single 0. The other thing is, you can see that MSB, most significant bit, if it is 1, then number is negative. If most significant bit is 0, then that number is positive. So this is also a nice property. So that means if I want to see whether a number is a positive number or a negative number, I need not to do any other calculation. I need not to, for example, subtract bias or do some other comparison. I can directly look at the most significant bit. If that bit is 1, then number is negative, otherwise number is positive. Okay, the other thing is that I can always find negative of one number using 2's power n minus of that number. So which essentially means that negative of a number I can find out using this 2 to the power n minus that number. So that means if I do further negation, that the number will become positive. So let's say if there is a number minus 13, I represent using this 2's complement notation. It will become plus 13, and then again I do negation, then again it will become 2 to the power, then again it will become a negative number. Okay. The other thing is range of the number would be minus 2 to the power n minus 1 to 2 to the power n minus 1 plus 1. I think there is a mistake here. So yeah, this should have been a minus sign here, not positive sign. So for example, for 4-bit numbers, the range is from minus 2 to the power 3 to 2 to the power 3 minus 1. So that means range is from minus 8 to 7, positive 7. So this is the range we get from 2's complement. And the other thing which can be proven easily, that addition, subtraction, multiplication all can be done intuitively, can be done using a standard binary addition method in 2's complement notation. So if I want to add two numbers, I can take 2's complement of these numbers can be represented in 2's complement notation, and addition of those numbers using a binary arithmetic will give me correct results. Although one of the number could be positive, one of the number could be negative, or both the numbers could be positive, both the numbers could be negative, it always give me correct result using the simple binary addition method. If I want to do subtraction, then the best way is that whatever number I want to subtract, I should take 2's complement of that number. So I should represent that number as a negative number. Let us say that number was a negative number and I want to subtract that number. So taking 2's complement of that negative number will become the positive number. So let's say the number was minus 13 and I wanted to subtract this minus 13. So after taking 2's complement of that minus 13, it will become plus 13. So that's how this negation rule is helping me, that I can do the step would be, first I need to take 2's complement of that number and then add it like a regular addition. And interestingly, even if I multiply two numbers using 2's complement, then the result will always be correct. But here a caveat is that there is no overflow assumed. So that essentially means that if I am adding 4-bit number, I am multiplying 4-bit number with another 4-bit number, the output should not be more than 4-bit, then the result would be correct. Otherwise it may not be correct. So there are always ways to fix it. So that's why multiplication is also workable, or is can be worked out using this 2's complement arithmetic. So I can understand that it's because it's all theory or using formula, it doesn't sink into our mind. So let's take some examples and see that how addition or multiplication will work. So we'll start with an addition. Let's say I want to add a 13 and with minus 3. So first I'll do is I'll represent 13 in 2's complement notation, because 13 is a positive number, and here I am assuming 8-bit numbers. Okay, this method of 2's complement work for any number of bits, but I am showing it using 8 bits here, so it is just an example. So first I represent 13 using 2's complement because it's a positive number. I need not to do anything for sign bit, and 13 I would represent as 1 1 0 1, and I am appending the rest of the most significant bits as 0. Now I want to represent minus 3. So for representing minus 3, first I have to calculate 3, that means 1 1, and then or basically 6 zeros and then 1 1, and then invert it. Inverting it will become 6 ones and then 0 0, and then I have to add plus 1, so that will give me minus 3. 1 1 1 1 1 1 0 1. Now because I want to add these two numbers, so I am adding 1 plus 1 is 0 and there is a carry of 1. So this, because this is 0 0, carry would come directly 1 here. Then again 1 plus 1 is 0, carry is 1. 1 carry plus 1 will give me a result sum of 1 and carry is 1. Because carry is 1, plus 1 will give me 0. Again carry is generated, 1 plus 1 0, again carry is generated, 1 plus 1 0, another carry is generated, 1 plus 1 0, another carry is generated, and we finally will have a carry here. Now carry here, we have to ignore this carry and we can leave this carry. We can simply discard this carry without worrying about the results, and the remaining 8 bit gives me correct result. So minus 13 minus 3 essentially is 10, and that's what we can see from this number. Let us see another number. Let's say I want to subtract a number, 13 minus 5. So again what I'll do is 13 and then take 2's complement of 5 and then add these two numbers. So essentially all subtraction would be converted into addition. Okay, and there is no so because negative numbers would be represented in 2's complement form, everything is addition here. Now in the same way, because in the same way if I do this subtraction, then I would get a correct result here. So 13 would be represented by 0 0 0, 1 1 0 1, and 5 minus 5 would be represented if I will calculate. So minus 5 is 1 1 1 1 1 0 1 1. How do I got it? So basically 5 is 1 0 1. If I inverse it, it will become 1 1 1 1 0. This is 1 and then 0 1 0. 0 1 0, and then I have to add plus 1 out of it, so it will become 1 0 1 1. So this way this minus 5, 2's complement of 5 would be calculated, and if I add both of them, then 1 plus 1 is 0, carry of 1, and this carry of 1 I add from to 1, then it is again 0, carry of 1, and this carry is added to 1, so output is 0 here. Now 1 plus 1 plus 1, sum is 1 and carry is 1, and now carry would be propagated here. So this will all be 0 0 0, and there would be one additional carry. Now let us see how will it work for multiplication. So here, to make my life simpler, I am taking 4-bit number, so there will be only 4 partial products. So let's say I want to multiply 2 and minus 3. 2 is 0 0 1 0 and minus 3 is 2's complement of 3, that means 1 1 0 1. Okay, so if I multiply using this, how do I multiply? So first bit 1 I will multiply with this multiplicand. First bit of multiplier is multiplied with multiplicand 0 0 1 1 1 0, and then I will shift, I will put a cross here. We remember all our decimal multiplication tricks. So because multiplier, second bit of multiplier is 0, so we can simply say 0 0 0 here. Now the third bit of multiplier is 1, so again this 1 would be multiplied with 0 0 1 0, and I leave 2 places. That means 0 0 1 0, and then 2 places are left blank. And for the last bit of multiplier, it is 1. Again here I will leave 3 places blank, and then I will write the same multiplicand here 0 0 1 0, and finally to get a multiplier output I will add these 4 partial products If I add, then 0 can be directly come here as 0, and this is 1, and here in this row these are all 0, so output is 0. In this row there is only 1, so output is 1. In this row there is only 1, so output is 1. So similarly we can do this partial addition, and because as we mentioned earlier, we are not going to consider overflow, only because my input was 4-bit, this was also 4-bit, my output I have to consider only 4 bits. So the output is going to be 1 0 1 0. So if I translate this 1 0 1 0, it is going to be -6 in 2's complement notation. So this essentially gives us a confidence that yes, using 2's complement we can represent any numbers, plus we can also do this binary arithmetic addition, subtraction, multiplication using simple operations. Or whenever we are doing operations, we need not to worry about the sign bit or the underlying representation, underlying representation of negative numbers. Underlying representation, if it is 2's complement, it is always going to give us correct results. So there is also one thing again we have to note down, that when my results are going to be wrong, that also we should be clear. So whenever we are going to cross that breakpoint or discontinuity of my number circle, then I am either going in overflow condition or going in underflow condition. So this, unless we know this overflow underflow condition, we never know that my results are correct or not. Okay, so if it is overflow, that means number is outside the range of numbers that can be represented using that many number of bits. So for example, if it is 4 bits, then I can only represent from -8 to 7. If my addition result is more than 7, I can't even represent using 4 bits. So that's why whatever result I am getting, it may be wrong, it may look wrong. It's not actually wrong, but it may look wrong because this number I can't represent using that many number of bits. So how to identify this condition, that's very important to know, and important to practice or see also whether I am not reaching an overflow condition. So overflow condition is a very can be laid out or can be put in a very simple words. If addition of my two positive number is resulting in a negative number, that means there is an overflow. So for example, in a number circle, I am adding 5 plus 4. 5 plus 4, and I am representing only using 4 bits. So 5 plus 4 will result in 9, and using 4 bits I can only represent up to -8 to 7. So 7 is the maximum largest positive number that I can represent, but my output is 9. So that means whatever output my binary arithmetic will show will not be correct. So I have to raise that this is an overflow, this result is not correct. So to check this condition, if sign of both the operands are same and I am doing addition, and result is either of opposite sign or a result is 0, that means it's an overflow. So similarly for negative numbers, adding negative numbers, so -3 minus 7, it is going to be an underflow. Okay, so this is how we can represent overflow and underflow. And we also can clarify one thing, that if the signs are different, one number is positive, another number is negative, and we are adding these two numbers, there can never be overflow or underflow condition. So the number which is larger is going to win. So for example, I am adding plus number plus 5, and I am adding -8, plus 5 and -8 I am adding. So whatever number is larger in magnitude your number will become of that particular sign, but it is not going to be overflow or underflow. So this symbol condition check can tell me what is the overflow or underflow condition. One more topic or one more point which I would like to touch upon here, that a negative number, if I have to convert n bit number to m bit number, it's going to be slightly different here. So let's say I want to convert a 4-bit number into a 8-bit number. If number is positive, it is going to be same. But if number is negative, then it can lead to a different representation. It can lead to a wrong representation. That's why we call it as a sign extended number. So in a sign extended number, let's say 1101 is a 4-bit number, which essentially represents it represents -2. So this -2, if I want to represent in 8-bit, then I need to remember that because it is -2, so its sign bit has to be 1, and -2 would in 8-bit would be 2 to the power 8 minus 2. Okay, so that means that this either I need to recalculate this number, or the easiest or a trickiest method would be that whatever is the sign bit here, if I extend that sign bit to the larger, like rest of the MSB numbers, let's say m bit is larger and n bit is smaller, okay, then m minus n bit I can extend as a sign bit, then the number representation would be correct. And this sign extension will work even if my sign bit is 0, because then I would be extending zeros all the way. If sign bit is 1, that means I am extending it for the negative numbers, and it would give me an easy method of converting from 4-bit number to 8-bit number, or 8-bit number to 32-bit numbers. The representation is fast, and otherwise the ideal method would be, I had to do, for example, I need to convert from 8-bit number to 32-bit number. I need to subtract that number from 2 to the power 32 minus the magnitude part. So this sign extension trick can make it little fast. So here I would like to close, and I can summarize that overall in last half an hour 45 minutes we have understood what could be various ways of representing negative numbers. So one thing you may be thinking at this point, that if we are not going to use 1's complement, sign magnitude, 2's complement, why we are studying all those things, or why was the only motivation to study those things were to find flows in all those numbers? We can here I would say that it's not like that. Each of them has its own purpose or its own qualities. Sometimes we do use sign magnitude number also, sometimes we do use offset or biased method of representing negative numbers as well. We'll see in some of the later classes that how do we use them. Okay, the other thing which we have learned in this class is how to do arithmetic operations. So this class would remain incomplete unless we do practice a lot of questions, or we do some of these things ourselves. So I would be posting a tutorial after this class so that you can work on those questions. Some of those questions I would put as a solved questions, and some of the questions which you will try to solve yourself. Thank you very much.